Especially because the newest iPhone is $1,400.
I think that's part of
Yeah. Well, also because it's like the S.
Okay, come in.
All right. All right. Hi, everyone. So we're about to start. Thank you all for attending our second deep learning meeting. We have a great talk tonight and an amazing speaker, Orla Fanning. I'd like to thank Mission Link for sponsoring the event and paying for the space and food and drinks. So Mission Link is a deep learning platform for computer vision to help you manage your resources, data, and experiments all in one place. I'd also like to thank Samsung Next for sponsoring the event as well. And the recruiting team is in the back, so if you're looking for a new gig, talk to Vidya. Over to you.
Yeah, again, thanks for coming. I'd just like to introduce my good friend here, Orly Tani. And there's a lot of things I wanted to say, so sorry, but I'll read it out. So he's a postdoctoral fellow at Stanford University and Facebook AI Research. And today he's advised by Professor Leonidas Gibas and Professor Jitendra Malik. You'll correct the pronunciation later, right? So his main research interest is in 3D deep learning, shape analysis, and learning with limited data. And he's received multiple awards for his work, including the Weinstein Prize for Graduate Studies and a Best Paper Award at SGP 2016. Make sure to catch him at the workshops and tutorials he organizes for deep learning and geometry. And without further ado, Orly Tani.
Thanks. Thanks, Yuval, for the kind introduction. Actually, when you mentioned there's going to be free pizza, you didn't mention I have to give a talk as well. But I'll do it anyway. So today, as Yuval said, I'm splitting my time between Stanford and Facebook Research. Pretty exciting times to work on geometry. When I started working in the field, so when I started my PhD, at the time I finished my master's in this topic of geometry, and at the time deep learning kind of entered and started, taking over the entire field of computer vision. And at the time, geometry people, and myself included, we were kind of, it felt like we were handling very interesting or mathematically interesting, but very toyish sort of problems. And I remember seeing the impact and thinking, oh, wow, wait, this is real now. We can actually use this machinery and do something. And along with that came tons of new 3D data. And as they say, with great data comes great responsibility. So we had to start making sure that there are tools to accommodate that. So in today's talk, I figured I know you people come from different backgrounds, so it was a little bit hard to come up with one coherent talk. So I figured I'll give some background so everyone's familiar with the basic machineries that we have. And since I am fortunate enough to work with those people that are developing, advancing the state of the art in those methods, so I will mention those works as well. And depending on your questions, you can lead away the talk to whatever you feel is nice for you. So I hope my next sentence is not going to be too controversial, but I argue that even though we sense the world in 2D and we walk around with our cameras, 3D is a much better representation of the world, right? What makes more sense, right? To keep one model of this building or take 100,000 images of it. So until recently, as I just said, in this field of geometry, whenever people said 3D, we're kind of imagining these kind of things. So some graphic model and everything's very clean in a very clean scenario. It's suitable for computer games, but it doesn't grant us too much tools to handle real data. And then, things changed. So we started having this developing consumer market, and suddenly getting a scan of yourself is, it's going to take a few seconds, and suddenly you can, I don't know, print yourself, a model of yourself to keep at home and play around with. Yeah, maybe I shouldn't have said that. When sensing 3D became much easier, we have things to do with it. That's very important, right? We want to watch it. We want to put our VR headset on. We want to play with it. We do want to print stuff. So as I said, what are we interested in when I say 3D, right? So I guess 2D image is a good reference because it's like, everyone's more familiar with that. So in principle, similar tasks, we want to be able to have, first of all, a large data set. We want the equivalent of ImageNet and COCO challenges, but in 3D. So that's one of the things we're working on, collecting tons of data. And then what are interesting questions we want to ask about these data? We want to be able to classify it, split it into different categories. It's interesting to discuss parts, right? These are many objects share parts in common. We want to be able to ask, maybe infer, what materials these objects are made of, things like that. So we need a knowledge base, and we need to design methods that can help us solve this question and answer these questions. So as I said, I guess most of you in the room, if I have you design a new face detector, a new image segmentation algorithm, or just make something that kind of works, I guess you'll handle it, right? So it's kind of solved. I don't want to insult anyone doing 2D deep learning, but it feels like at least we know what to do with this sort of data, right? What about 3D? Well, I'd argue that we have a very fundamental problem, right? Besides not having enough, the same amount of data and the same amount of problems, all those things. We have a more fundamental problem, which is how do we even represent this data, right? There's no standard in the community to what's 3D. I keep saying that, but what do I mean, right? So just to give several, examples. So point clouds is, I guess, kind of an intuitive 3D. Many people think of point clouds when I say 3D. That's how we picture, a lidar situated on the top of a car driving around. Probably many of you are familiar with voxel grids, which are maybe the most natural lift of pixels to 3D. But there are other representations, meshes that we all know from computer games, and even level sets. So we haven't even decided on that. The first works that try to, tackle these 3D problems, I guess what people had in mind, and it's not like I've been there with those people, but I guess what they had in mind is like, all right, so we have a strong hammer, right? The convolutional neural network has proven, by that time, has proven to be quite powerful. Why not just treat our 3D data as yet another nail and just hit it with our hammer? Let's see what happens, right? And I mean, it's not a disaster, right? It kind of works, but so what do I mean by hitting it with a hammer? So let's say one option would be, let's take a 3D model and turn it into images, right? I said before it makes less sense in terms of representation, but still, if we have a good way to work on images, we can just do that. Another option is let's take our standard CNNs and just add another dimension. It's a tensor anyways, right? What does it matter? So the first solution I mentioned is, again, so as I said, you take your 3D model, you sense it with cameras, you render the images from around that model, and you feed each image into its own CNN, right? And then you kind of combine the output somehow, and you can ask your standard questions. Some fully connected layers will tell you how to classify it. Besides some technical difficulties here that needs to be resolved, like how exactly do I aggregate these? What happens, if I rotate this by a certain degree? Suddenly the order is not consistent anymore, right? There are some technical difficulties. I don't want to get into those. There's a more fundamental problem, right? One is this is very clean, right? There's an assumption that we can render. So as if I said, this is not a point cloud, for instance. Another problem is that we assume to have access to those different, we need to be able to walk around each individual object. Here I'm showing one object, but what we really care about is inferring entire scenes, right? So there are more fundamental problems for why this method can't solve all of our problems. With this guy, it's another issue, because I feel like, given enough memory, in some sense, and maybe my colleagues will kind of hate me for saying that, I feel like if we had no memory issues, this was, the way to go in some sense. Enough data, enough memory. My bet is that was gonna work. But what do I mean by not having enough memory, right? So here's an object, and now let me represent that as a voxel grid. right? And when I say a voxel grid, here the numbers should tell you I'm splitting my space to 32 by 32 by 32, and I'm going to decide for each cube whether it's occupied or not. If I do so, and here I'm gonna gradually increase the resolution, and here I'm reporting what percentage of the space is occupied by these voxels. And as you can see, when we start getting to resolutions that actually make sense in nicely representing the object, we're very sparse. So plugging this into this one additional dimension CNN sort of thing that I said before, will grant you that like 98% of your kernels will be fed with zeros. Right? So that's probably the major problem here. And in this doc, I want to focus on two other representations that I think are very interesting and have lots of merit. One is the mesh, and the other is the point cloud. And I'm going to start with the point cloud. So as I said before, I guess a good picture to have in mind when I say a point cloud is something that gives you a point cloud from the raw sensor, right? So you have a LiDAR, it gives you point cloud. That's nice to think of. But you can also think of having a mesh and sampling that mesh to turn it into point cloud. Maybe it makes less sense, but it's also an option. So let's build a neural network to consume that can be fed with point clouds, right? What are the problems of such a design? Why is it not just a CNN? Well, there are two problems with this point cloud. One is that it lacks structure, and the other that it lacks order. And by structure, I mean images are nicely situated on a regular grid, right? Our points are no longer on a regular grid. So we need to accommodate for that somehow. And order is, again, in an image, you have a natural order. If I tell you that I take my kernel and I move it 1 pixel to the right or 1 pixel to the bottom, everyone can picture what's going on there, right? But with a point cloud, again, you don't know what's the order. But you can artificially introduce order, maybe a lexicographic order, right? Let's take the XYZ plane and just sort the points, right? So now I have a chair. I sorted the points from X to, let's canonicalize that chair. I sort the points from X to Y and in some lexicographic order with the axis. But now I have a new scene and I have another chair next to it, right? Suddenly, what happened to the order, right? That doesn't make sense anymore. So we have a fundamental problem here. The first method that kind of, I'll say, revolutionized the field of point clouds is a method called PointNet. And the basic ingredient that is built on is a symmetric function. And a symmetric function is simply a function that doesn't care about the order of points, right? It will give you the same value no matter how you permuted the points. So you have points x to xn, our point cloud, and we gave it some order, and now I shuffle that, and I reorder the points, the function will give me the same value. And it's very easy to think of such examples, right? A max function is such an example, right? A max value doesn't care about the order of the points. A summation doesn't care about the order of the points, right? So these functions do exist in nature, right? The other ingredient is order-independent transformation. And what do I mean by that? Very simply, you take your n by 3 point cloud. So you have n points, 3 because we have x, y, z, right? Just 3 dimensions. And we feed each point individually to some function. Here, MLP stands for multi-layer perceptron. But just if a function works separately on each of the points without interacting between the points, then we don't have to worry about the order, right? What went in in whatever order it went in is going to have the same order when it comes out. So this ingredient is kind of intuitive, pretty straightforward, and I skip a couple of layers such as this one, but the concept remains the same. And here, once we can go ahead and increase the dimensions. So we start with n points, each has 3 dimensions. We can increase that point here to 64, later on to 1024, and then we have our symmetric function. In this case, a max pool function. And when I say max pool, just we're all on the same page, right? We take every dimension and just take the maximum value of all the points, right? So just the max of that column and the max of that column. So I'm gonna be left with just one global feature vector that represents whatever I had in that cloud. Are these two ingredients clear? Cool. That's great. Because this is basically PointNet, right? So one question that you can come up with is, all right, well, so you told us about a few ways to keep the ordering intact or not caring about the order, but is it good enough? Like, are we really able to capture, the function, the real function, the natural function, the one we're looking for, that takes this point cloud and tells us, I don't know, that that's a horse, right? And in that paper, the PointNet paper, showing the universal approximation, and basically what they're showing is that given enough k, so if this 1024 was large enough, I could potentially get as close as I want to the actual function that we're looking for, right? And if we have time later on, I'll give some more intuition about why that's the case. 2 words about those bells and whistles that they added, to this architecture. So as I told you, the input points were n by 3, and right before it is passed to a multi-layer perceptron that works separately on each of the points, it goes through a transformer network. For those of you who are not familiar with transformer network, it's basically, you branch out to try and estimate one global transformation that will be applied to the entire point cloud. Now, put that in a more intuitive sense. Imagine that I give you a chair, a point cloud representing a chair, and then tomorrow I give you the same point cloud, but rotated by 30 degrees, right? What this is expected to do is to canonicalize all the input, both of those input examples, because we are working on the three dimensions, the x, y, z dimensions. So we do want these points to be the same, right? So this is how you can think of this transformer network here. Later on, there's another one, slightly less intuitive, because that one is already working in feature space. So at the point where we're not really sure what's going on anymore, right? And another thing, and this is what I showed in the previous slide, so the global feature that we got from the Mapu operator. And I'm going to pause right here. This feature vector gets us back to the point where we know what to do in neural networks, right? So we do that with images as well, right? We take our image, we get to a point where we have a global feature vector, and then we can ask to classify that image, right? So basically, we got where we wanted, in some sense, for point clouds as well. Now, let's say that we wanted something slightly different. Let's say that we're interested in labeling each and every point, right? We want to say something about each and every point, not just that. Yeah, I was hoping, not just that this is a horse, but let's try and label each of those points of the horse. Maybe segment this into parts or something like that. Then we need to go back to the full resolution somehow, right? So a neat little trick that these guys are doing here is they take the global feature and they concatenate it to each of those points. Now, why is that useful? Because intuitively, up until here, each point was individual. It was not aware of all the other points. So what can he tell you? Here's a point in space. That's not a lot of information, right? Even if you take it from 3 dimensions to 10,000 dimensions, it's not more information. No more information there. But if you concatenate the global feature, suddenly each point is aware of some global notion of what the other points are doing. And processing this from here is actually adds information. And if you keep a full resolution here, then you can say something. Then you can get a different label per point that's meaningful. And you can train for other tasks, like segmentation, for instance. Is that clear? All right, cool. So I don't want to get into exactly what that challenge was. I just want to show some differences where these guys presented PointNet, and they showed similar performance with just that point cloud to what you would have gotten with a volumetric representation, which is much more wasteful, or there's multiple images. So that's a nice proof of concept that we can, if we were suspicious a little bit about that symmetric functions and how well we can do with that point cloud, with pure PointNet, this kind of tells us there's something to it. Now, this is a very nice experiment that these guys show in the paper that I thought would be interesting for you guys to see. I really like this one because this kind of gives us some intuition on what's going on there. And specifically because we're using a max function, there's a nice explanation to what's going on. So what's happening here? These are the original clouds, right? And it's just colored by the location in X, Y, Z. And what these guys are doing is, so remember the global feature? That was the output of a max operator that was working column-wise. What we're going to do is we're going to take those points and start removing them. And the rule is that you're allowed to remove every point as long as you don't hurt the max operator. And that's OK, because many points can go away, right? And as long as you don't hurt the max operator, the classification, say, of that point cloud will remain the same, so you haven't touched it. So it kind of reveals what's the critical point set that will cause the network to decide whether this thing is a table or not, or whether this thing is a pistol or not. So I think this gives a little bit of intuition that the network actually, picks up on those boundaries and significant features. And the last row shows the other experiment. So you can go ahead and add points as long as you don't change the max pool operator, right? And this gives you like a super resolution algorithm, if you will, right? Or how crazy you can go and still remain with the same instance to be classified by the network. Here are some results of what people are actually using PointNet for. So this is an example for a challenge where you want to take a point cloud of a 3D object and be able to break it down into parts. So you want to label each point according to the part it belongs to. So in here you can see that the network is able to split each of those to meaningful parts. And here it's a demonstration of the same thing, but with partial information. So this demonstrates that the network doesn't always need to see the entire shape, but it can also handle some missing parts as well. This is a more realistic and probably more interesting example, right? Where the challenge here is to take an RGB, a single view of an RGBD scene, right? So you have RGB and you have depth, and you want to output a semantic labeling of that scene, right? So all the chairs will be denoted in red, floor in blue, et cetera, et cetera. So we can see that this thing even works for entire rooms. Right, can we do more? Right, so we know to classify, and we know to label each and every point. But here's a little problem that we might be interested in. I'll give you a 2D image, right? And you want to be able to reconstruct a 3D shape out of that 2D image. So this has also been demonstrated to work nicely with this architecture. So to consume an image, we all know, right? And to create a point cloud, now we learn how we can do that. What's the problem here? Here's another example of, instead of an image, I give you a partial information, and the task is to, again, complete that partial information. What are we missing here? Well, let's say that I give you a mesh, and I sample it, so you have the full point cloud, and then I give you some virtual scan of that. So that's a partial input, and you want to be able to complete it. You pass that through PointNet, and you get a point set, and you also have the ground truth point set. But differently from images, we can't just put one image on top of the other and measure, an L2 distance, right? That's a problem. So instead, I'm going to skip a few slides here. Instead, what we're going to do is imagine that this is in green here is the ground truth point set that we're interested in having, but the orange one is what the network had built, right? A loss function that's useful here is called the chamfer distance. It's basically you take the closest point, each orange point looks for its closest neighbor, and each green point looks for its closest neighbor, and you sum up those distances. And this is what's called the chamfer distance. Without going into details, it's not precisely a distance, but let's not delve into this. All right, so some real-world examples of utilizing this such architectures is, as I mentioned before, you take a 2D image of an object, and you're able to reconstruct a complete point cloud of that object. Since we're back at the zone where we're comfortable and we have a latent representation, we can do other neat things. So for instance, we can build an autoencoder. Namely, we can take a point cloud, get some global feature representation, and reconstruct that point cloud. And now we can take the latent representation of this guy and the latent representation of this guy, and just interpolate between them. Just take a convex combination of the two representations and reconstruct those. And that's interesting because this lets us explore the latent space of what the network has learned. And we can see that it's not garbage, right? So we're seeing something more interesting than just an extrinsic interpolation between this guy and this guy. We're seeing actual, some of those look like actual creatures that could exist. Lastly, we can go on without a generative model, namely GANs. And the same goes for here. We can randomly sample and generate from a latent vector and get meaningful objects. So we're learning something on the space of shapes here, represented in space. Any questions? Yeah.
How many models did you have to give it to learn that latent space?
Here, you mean?
Yeah.
So, if I'm not wrong, a useful, in most of those works, in these synthetic examples, right, what's used is the shape net. That's the largest data set nowadays with synthetic objects that you can actually work with. So you can sample those. And it's a tricky question because it has several tens of thousands of shapes, but you get some natural augmentation by resampling those. So in some sense, you can think of that as more examples. Yes?
Is there a way to have intuition on the blending between two shapes? You're blending from one type of table to another, blended nicely through things that we would think are reasonable interpolations. Is there a way to have confidence that, of course, it would be that way as opposed to blending in a really non-representational way?
Do you mind waiting with that question That's a very good question. I think it's very general in the field of deep learning, and I think I have some applications that I want to delve more deeply into, and then I'll open this again for discussion. All right? Yeah. Yes. Yeah. So the question is like, what's special about that? If I want to summarize that, so I'm going to say computational efficiency is the main reason. If you want to use the proper distance here, you'd have to use the EMD, the Earth mover's distance, which is basically the same, only with a bijectivity constraint here. That's more complicated to solve. Plus, it has some other. I actually have some slides about that. I don't know if I want to break the presentation for showing those slides. Maybe we can, after the presentation, I can just go back to that point and show you those slides, because these are showing interesting experiment replacing the proper distance, the EMD, with the chamfer distance, and some interesting things come up. Just not to keep you too anxious, the EMD will give you some kind of an average distance. So if you introduce some discrete distribution, so a bunch of shapes with a non-smooth transition between them, the Earth mover, and you will ask for one representation for all those shapes. The Earth mover's distance will give you some average shape. Well, this guy will actually capture this discrete distribution in some sense. It will make more sense with the images. I'll try to show them afterwards. All right, so we've seen what can be done with points. Aren't we missing something, right? So yeah, of course, we're missing edges, right? The points need to be, sometimes the points are connected, right? This is very useful information. Why is this useful? Many reasons. First of which is sometimes we just don't know what that point cloud is if we don't know how to connect the points, right? A second thing, I still don't want to go there. The second thing is it's just more concise. So imagine that you have a flat plane and you want to represent that. You can represent that as two triangles if it was a mesh, right? But if you want a point cloud, you can't just use 3 points because these are not aware of each other's existence. So what will you do? You will sample that plane, what, 1,000, 2,000, 3,000 times? It's much more wasteful. So, and lastly, once we go into non-rigid deformations, the connectivity is super important, right? Because in Euclidean distances, these points are neighbors, right? But if you go and bend this guy, then you want to be able to say that this patch here is the same as this patch here, right? If I have these two hands, we don't want to treat them in Euclidean space, right? If you just measure Euclidean distances between the points, these are completely different objects. Do we really need to work hard and have the network learn each individual deformation of the hand and treat that as a new representation and a new model? Because that's what will happen if we'll have a point cloud. And instead, if we can somehow exploit the connectivity, then these are not new creatures. These are very similar creatures. And just kind of like so you don't think that this is fake or something, that having connectivity is something that's not plausible. Here are two very useful examples of where we do have connectivities. One is the social graph, right, where we know how to connect users by friendships or whatever, common interests. We know how to connect products. We know how to do all those things. And 3D shapes, which are very useful, either as an input, things we want to process, or, and I'll show us a few examples of those, sometimes the input will be an image or a point cloud, but we'll be interested in reconstructing the graph. And that's again, that calls for some method that allow us to work on points and connectivities. Okay, so how do we design some convolutional neural network that cares for both points and connectivities? What are the useful features of a CNN in 2D, right? The standard ones. The one, we want to have convolutional filters. So more like we want to reuse weights. That's the strongest thing about CNNs, is that you can take weights that were useful for you in some places in one image and reuse them in other places in other images or the same images, right? Co-occurrences of filters, of patches is one of the building blocks of computer vision since the early days, and the CNNs are building on top of that very heavily. So that's something that we do want. We want to be able to compose them, right? So a single layer CNN is not that useful, as we all know, right? We need deep networks. And finally, we care for locality. Again, going back to this idea of reusing structures. Structures tend to repeat more in local neighborhoods than in global neighborhoods. So here's a very easy to remember recipe of how to exploit connectivities, and it's pretty intuitive. So if you have a graph and has n vertices, each of them has some function defined on that graph. Could be an XYZ location, but could be some other function that is interesting here. So our representation is n by d, n points, d dimensions. And we have also the edges between them, right? So what we need is a function that is parameterized by a set of parameters that are going to be learned, right? We'll denote them by theta, that can consume the points we're at currently, the neighboring points, j, and the edges that connect between them. Then we need to aggregate this information somehow, right? So we'll want something that's permutation invariant here, and that operator is just that square over here. And that is basically our local operator, right? That is the most similar one that we can think of as you would use in a standard image. If we, instead of doing it separately, we'll do it for all the pixels in the image, we can denote that by some a of theta. Then all we're missing is some nonlinear function to pass that result through. And that is the basic recipe of the graph CNN. And these come in many flavors, but it all boils down to these guys. So here's an example of a patch operator that has been very useful specifically in the first works of non-rigid shapes to detect correspondences between non-rigid shapes. And as you can see, this is like I'm showing here 3 different ways to construct such a patch, where what we care for or what's different between those 3 is the way we explore our neighborhood. So this one is just an isotropic distance. We don't care where that point is. We just know how far it is in geodesic distance terms, right? Here, we actually can differentiate between different directions, and the way we do that is by using some local geometric value on that shape. For instance, the maximal curvature will define a direction, and then according to that direction, we can start measuring angles, and we can combine both, right? Both radius and directions. And as you can see here, once you know how to extract a local patch, you can do the same as we did in images. You can just learn your kernel and perform a convolution between those. So as I said, the interesting application that this was used for is to find correspondences between shapes. When I say correspondences, I mean that given a pair of shape, let's say this woman here and this guy over here, you want to take every point on that woman and say which is the corresponding point on that guy, right? And if it was accurate, it's going to be painted with white, so it's zero error. And if it's very far off, this is measured in percentage with respect to the radius of the entire shape. If it's very far off, it's going to be painted black. So as you can see, this got very nice results in this paper from Federico in 2017. It's no longer the state of the art, but it was kind of a breakthrough. And this is showing what happened since classical methods that were trying to solve correspondences. And this is random forests. If any of you is still using that, right? So in academia, it's kind of like a forbidden word to say now. I know it's kind of useful in Kaggle contests, but I haven't touched that for a couple of years now. And here you can see what happened when all the deep learning algorithms kicked in, including our method here that is currently almost saturating, this making this benchmark almost not useful anymore. And here, yeah, I just couldn't resist putting a recent result we had just because of the cool figures. But this is doing the same performance as this guy, but in an unsupervised fashion. And if anyone is interested, I can share more details about how to do that. Interesting application, and the result is just so that you understand what you're seeing here, except for nice colors, is that similar colors represent matching points. Is the purpose of that coloring. And here's the application. One of the most useful applications is texture transfer, right? So I can scan a guy, and then I can put a Facebook T-shirt on him, a Stanford T-shirt. And this shows that the same can be done with partial scans as well. So that's very nice because, again, as I told you in geometry, the assumption of having a complete shape was used so extensively that finally seeing something that goes towards real life examples like actual scans is very reassuring that the deep networks can consume this point cloud, this mesh, and still say something meaningful about that. Right, so now I want to delve, let's see, how am I with time? I think we have time to go into details about that. So now I'm going to share a work that I had in last CVPR that I think utilizes this machinery of learning on graphs and manifolds. Right, so the task here was, just from my perspective, was after doing so much shape matching, I got to this internship at Google, and I told my host, look, I'm tired of doing one more shape matching problem. In every shape matching paper that I had, the first sentence would say, shape matching is so useful because we can do A, B, C, D, and then a list of stuff. And I told him, let's do one of those stuff eventually. I want to just try that once. And so we figured a shape completion algorithm would be nice. And when I say shape completion, what do I mean? I mean that given some kind of partial input, could be a mesh that's missing some limbs, could be a point cloud scanned from this direction, could be that the partiality comes from the viewpoint. That is probably the most natural way of partiality. And this is from actual scans, never mind the architecture of that sensing device. And what do we want? What are the necessary things we want out of this completion algorithm? Well, first of all, we really cared for non-rigid deformations. So as I told you before, we don't want to handle, if a person moves, don't want to treat this as yet another person, right? It's not like a chair that has arm wrists or doesn't have arm wrists. It's a much more fine grain. It's me and then me moving my hand here. If these are two different creatures in the world, we need so much capacity in the network. So non-rigid deformation. We want to handle, as I said before, different types of partiality. So we want our algorithm to be agnostic and not clinch onto just this type of partial views. We want variability in completion, right? So if I took off the limbs of this guy, there are many ways to impute them back. And we want to capture those different ways. We want some completeness guaranteed because, I don't know, maybe I gave you a partial scan, but you want to use that constructed mesh in a physical simulator with fluids or smoke or whatever. You don't want the fluid to go through that hand, right? Oh, this is actually plays. And lastly, there have been works doing this manually. So people are important enough to model precisely, but maybe you want to work on, I don't know, some kind of animal, and we're not going to do each and every animal, build a new model for that. So here's the basic network backbone that we've used. So this now, after you've seen the recipe for constructing a graph neural network, you can identify already some similarity, right? So the output of a layer at that point I would be. I'm not going to get into all the details here, but the output of the layer at the point I will look at the neighborhood, all the neighborhood vertices and neighboring vertices xj, and gonna take a filter, apply it to each and every one of them, and aggregate. And you can do that many times in many channels. And basically, the aggregation is what you get in the end. So it follows exactly the recipe I said before. And the only thing that will change is how you design that function, the parametric function that consumes these two vectors. So one option, for instance, will be to have a function of xi minus xj. That will make this translation invariant, right? Because if you took the entire cloud, the entire shape, and each x here was the xyz position, and you shifted it, nothing changed, right? Because the input to that function, the parametric function, will be always the difference. Never mind, it wasn't clear. It's just a detail. And now I'm going to try and a little bit answer the question that you had before. So what was the idea? As I said before, we didn't want to rely on knowing the type of partiality, right? It could be useful, don't get me wrong. Let's say that you want to design an algorithm that completes shapes that you always see from a single viewpoint. There's merit in knowing that information, right? That's a particular type of partiality. You never have a chair and just take off one leg and want to impute that back, right? You always know you can learn the type of partiality from data, and that's important. But we didn't want that on purpose. So what was the idea? The idea was, let's not introduce partial shapes at train time. Let's only rely on complete shapes at train time. And the idea here is let's take our shape, let's say this guy, right? We pass it through the network. Again, and I said that the backbone here is a graph neural network. But what we care about is that latent space that you asked about before. We want to put that point here in latent space. And this is called a variational autoencoder. We want to later sample from that latent space and reconstruct, and hopefully get the same input or something very close to that input. And what we were hoping to get from having this representation is a meaningful latent space. And when I say meaningful, we were relying on what you asked before. We were hoping that if the network had only seen plausible people at plausible deformations, the only thing that the network can do if you sample randomly from that latent space is to generate another plausible person at a plausible deformation, right? And yeah, I wanted to mention, but never mind. All right, so this is what we relied on. So at train time, we only introduced complete shapes. What did we do at test time? Well, as I told you, we already have strong algorithms for identifying matching, right? Shape matching is the problem I was tired of solving. So how do we utilize it? So given a partial shape, let's say that red part here, we know how to find for each point on that partial shape a corresponding point on some canonical complete model. Okay, so how do we use that? We randomly sample a point here. That point passing through the generator will generate some random initial plausible person at a plausible pose. But because we know that person we know the correspondence between each point here and each point on the person, we can simply start moving those points toward that guy in extrinsic space, right? So if that point on the top of the head doesn't match that red point on the top of the head, we start moving it. And now what happens? We move it, but we backprop through the network. So essentially, a movement in extrinsic space translates to a movement in latent space. And here's the cool part. Because latent space only knows generate plausible things, if I had to thicken the left arm, the right arm will be thickened as well accordingly, because that's the only thing the latent space knows how to generate. So yeah, so this was the basic idea. And again, just to explore this latent space, here's an embedding of this guy here, an embedding of this guy here. And as we can see, what's changing is both the shape and the pose. And we're seeing some smooth transitions here happening between the two representations. Here I'm showing just the variability in completion that was desired at first. And now it's super easy to get variability in completion. What do? We just initialize from different points in latent space. Right? We just sample at a different location and run the optimization algorithm. So we reconstruct in different ways. Some competing methods. So you can work with there are classical methods that can try and complete shapes. It usually gives you some kind of like a penguin-shaped people. And this method is actually not doing that bad, but it has two problems. One is, as I mentioned, it's based on voxel grids. And here's a nice demonstration of what happens when you have a resolution constraint, right? So here we couldn't go too far with the resolution. Therefore, it looks a little bit more bulky. And the other problem, which can't be seen here because this tests for this single viewpoint type of partiality, but that network does treat each and every input separately. So it does rely on knowing that this is the type of partiality in some sense. And if we had to introduce all types of partiality, we'll have a much more difficult time. Lastly, these are some real examples, and not just for humans. We can do that for other types of meshes. So in this case, we took faces. Right. I just wanted to briefly mention a couple of recent works that are also interesting, because I said earlier that a mesh, the assumption that the input will be a mesh is a little bit restrictive in some cases, but in some cases that's not what we want. We are interested in having some the classical 2D images input, but as output we would like to get a mesh. So that also requires us, and many recent works take this path of starting with some mesh of a sphere, say, and then deform it throughout the network to get the desired output that matches the input image. Of course, there are problems here, like topology can change and stuff like that, but in basic principle, you have to have ways to work on, you have to have graph neural networks, is what I'm saying. Right. This is another neat piece of work that takes a set of images and tries to learn, again, by taking some initial mesh and learning the deformations from that initial mesh, takes a set of images and tries to reconstruct the mesh. This is the first work that I know of that also introduced some texture. Yeah, I really should have cited the authors here. It's my bad. What about, just one slide about the other interesting case. What about where the mesh is not known? Right, that's also interesting. So you might say, well, are you going back to point clouds? Sort of. Can we have point clouds but create mesh from the point clouds and then utilize graph neural networks, right? That would be kind of cool. So in this work, which is called a dynamic graph CNN, dynamic stands for exactly what I just said. You can connect at first the points using proximity in extrinsic space, but later on, as you start learning meaningful features, you can start connecting points by the proximity of their features. So this gives you some nice results, like, for instance, this one. Here, what the authors are showing is for each point on the shape, they're coloring the shape according to distance. And as we start, we see that the closest points are the ones that are actually close to it in 3D space. But as you go deeper into the network, you see that even though that point is closer to this one in 3D space, this one is denoted closer because in feature space it's closer. right? So it makes sense to connect those, so you can get long-distance relations. And this is a submission that we had that was thinking of another nice case where you are given the connectivity, but maybe you can't rely on that connectivity. Imagine, I don't know, a citation graph where each node is a paper and the papers are connected by which paper cited which. Some of these can be noisy. I don't know, maybe I forgot to cite someone and maybe I cited someone that I shouldn't have. So this tells us we need to know how to break connections that shouldn't be there. And currently all those graph neural networks, they don't provide machinery to do that because they assume that an edge is there to stay. So what we thought of is, would be cool to do look at the dual graph, where each edge becomes a node and each node becomes an edge. Then if we do a graph network, a graph layer on that, we can actually learn a new weight to a node, which is actually an edge, and then those with the lowest weights can be removed. So this is a recent submission. I'm going to mention briefly just a couple of works from our group at Stanford that I think that are coming up and I think are super exciting, just so you see what else can be done with point clouds and meshes and geometry and learning. So this work is the first that I've seen that tries to preserve topology. I mentioned topology earlier when I said you take the sphere and you try to make it into an airplane. That thing can cause problems, right? It restricts you to a certain topology, and it doesn't necessarily naturally represent the input image. So this one is trying to also optimize for preserving the right topology. I'm showing here a heart, and I'm showing that a nice reconstruction from classical algorithm actually shuts down the necessary holes that we know should exist, and the topology of the heart doesn't change between adults and young people. So this is actually important. In this work is a very neat little trick where instead of running a simple point cloud, point net on a point cloud input, you try and infer the regions of interest by imagining objects that could be there, right? So you take a point and you say, I have some clues from my environment that this might be a chair, right? Instead of doing a 3D bounding box, which is super inaccurate, let's try to imagine a chair that could be there, and then gather the neighborhood according to proximity to these points. In this work, it's called TextureNet, is designed to get a consistent representation of straight lines. In this scene, it should be very easy to identify the leading axis. So I should be able to, even if you rotated the scene, keep consistency in this in a representation. And this work actually finds those patches, as you can see here, right? And then what it grants you is the ability to work with much higher resolution. So texture, as I mentioned, is something that we start caring about more and more recently. This is one of my favorites. Is a new representation for 3D creatures, let's say, where you take a 2D image, and the idea in this paper was to find a 6D pose estimation, which is a classical problem in computer vision. That's less exciting to me. What's more exciting to me is the representation that these guys came up with here, because here they take the image, and instead of trying to produce the 3D point cloud, they put this in some kind of a normalized coordinate space, meaning that it's always a canonical. So it kind of gives you already correspondences between each point on that camera and every other camera that you will put in there. So that's kind of cool. This work is taking a point cloud and trying to break it down to register primitives to it. This is very useful in industry. So classical methods, they tend to break. In such cases, you can see that this should have been 2 parts, but here there was just, sorry, the blue one is just what should have been 2 parts, but it's just 1 part that was optimized for it. So they're able to actually, put the correct primitives and be very accurate in the way you put them onto the point cloud. Lastly, I just want to mention the SUMU challenge. This is an effort from Facebook research and collaborators, where the idea here is if any of you from wherever you come from are interested in trying to solve those problems. I think this is the first, I don't want to insult anyone. This is a very well thought through type of benchmark where the organizer here really thought of like what are the interesting problems, starting from the 3D object detection all the way through getting a mesh reconstruction of the different objects in the scene. So you will be getting an input as a color, 360 imagery of the scene, and the depth, and there are several different tracks where you need to detect objects, reconstruct the scene, and find the mesh, which is, it's getting harder and harder to do. Right. And this was basically it. So thank you for having me here.
Yeah, thanks. All right, well, we'll take questions. Make sure to repeat them so we can hear them outside. And yeah, go ahead.
Yes, 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 yes.
Could you go back to the incomplete scan?
This one? From this work or the point cloud?
The incomplete scan. Something that picture is not
The-
complete. Picture.
Forward or backward? Was it the point cloud or the mesh?
Yeah, something like that.
Okay.
That's fine.
Yeah.
Yeah. So so for the incomplete scan there,
This
I'm
thing.
I'm just wondering, what if that person actually only has one hand or one leg?
Oh.
Is your output is going to be two hands?
Yes. Yes, it will. It will. Yeah. That's a legit question. I mean, it is a problem. It doesn't know that it's to differentiate between an actual missing hand and a missing hand due to scans, and that's kind of a design choice, right? Again, as I said, you could train the network on one type of partiality, the one that comes from looking at a single viewpoint, right? If this was the type of partiality and there was no hand, and there were cases where people had no hands in the train set, the output will be able to reconstruct that. But because we chose to train the network only on complete shapes, the network doesn't know this is plausible.
Are you going to design something that's actually resolve this kind of problem?
I mean, the paper is already accepted, so probably. No, I'm kidding. I'm kidding. It's a legit engineering problem that if that's what you want to build tomorrow, if that's the tech you need, then there are ways to go about that. But am I going to do it? Probably no.
Okay,
Yeah.
thank you.
Yeah.
Is the chamfer distance, is that like an A-star algorithm or pathfinding, where like a point would try to find its nearest neighbors and then like I'm wondering, like, how is it predicting which of its neighbors belong to it and which don't, and would you be able to set that up in a GAN where you have some sort of competition between two different?
Wait. The first part, yes, you look for a nearest. What? There's two parts to that question, right? Yeah. First, again,
The first part is how similar is the chamfer distance to like a pathfinding or like A-star?
it's not okay. It won't be it will only be a pathfinding if you would solve it on a mesh, right? But this was for point cloud, so it's in Euclidean space. So you can just look at the different points and look for the closest one, just easily,
Right.
Yeah. And for the other part of what was the question about utilizing this for a GAN?
So the object, so would you have like each point is looking for like which points that are closest to it and which points plausibly belong to it, which points belong to its object segmentation? Like you're trying to figure out like which points belong to me, which points don't belong to me.
Oh, you want to weight that also by let's say, I don't know, if it closest but not from the same label, I should ignore that? Is that the type of?
Yeah. So if I can figure out there's a point that's close to me that doesn't belong to my set, then how do I like? Would you have?
Right. No, that's an actual problem. I mean, it depends, right, on the design of your algorithm. But imagine something similar in the idea to the dynamic graph that I was showing. So you have the point cloud, but you're already a little bit deep into the network, so you kind of know, you know something about each point. You can measure the difference in their feature vector and say whether you trust or don't trust that point, right? So you're not just looking for closest points in Euclidean space, but you also threshold or ignore those that don't share similar features to the point you're at now.
And the second part of the question was like, how would I'm just trying to imagine setting up like a competition between two neural networks. So these try to compete to sort of like deliver a more accurate object segmentation.
That I showed one example of that. So yeah, this is actually again a result from again. That was trained in a similar way. So it needed to generate a point cloud, and then that point cloud needed to be consumed by another point net that would determine whether this is a legit object from the distribution of objects or not. Right?
Okay.
Yes.
When when making digital characters through traditional means, one of the big challenges is getting them valid over a sufficiently wide range of motion. And so there are lots of motions that the body is capable of making that don't show up in lots of kinds of data sets. Is there an ability, is there a way to probe outside of the state space?
That's a great question.
Of these things, whether it's a body or any kind of a recognizer?
That's a great question. So okay, again, we discussed the latent space, right? And I even kind of like argued that one merit of having a latent space that is learned from the available data is that it restricts you from not ever producing something that can't be. But Mr. Don here is arguing correctly that there's a crucial problem here, because what if the data set only contains people that rose their hand until here, but you know that people can go up to here, right? So how do you generate this? Yeah, I took a long time to repeat the question. The answer is pretty short. I don't know of any way to have that feature except for adding a model, and that is kind of something that we wanted to avoid. You could think of other ways to hack it using additional information from 2D. So if that's easier to acquire, we can try and learn more from that. And yeah, I don't see other ways actually to resolve that. I mean, it's kind of like it has. You have to weigh the pros and cons here, right? Because like one thing that we got from here, we did interpolation experiments in this problem. We also tried extrapolation experiments. So we took we had the lag bent over here and straighten up to here because we had that sequence in our data set, right? And then I tried to take that vector and extend it further, and I was hoping to see if the lag can bend over backward with the knee, and that didn't happen. I was glad it didn't happen because I said, hey, that's great. It captured plausible motion of the human body. But as you said, if we never had something that even takes the leg up to here, then we would have thought the human body is restricted even more than it is. So yeah. Yeah. Oh, sorry. Yeah, go ahead. You're first.
I didn't quite understand how you feed the relationships between points into the neural net. Are you feeding their indexes or their actual?
No, they're actual feature values.
So like you'd have one point that's here, and then you'd feed it the coordinates of the guys around it. And then...
No, you don't. Yeah, you feed the easiest way to picture it is.
The first one has the coordinates. I understand that. But what about
the first layer? You mean?
The first point. Well, there's one point, and then it's neighbors.
Right.
How do you represent the neighbors in there? Are they their coordinates?
So you know which are the neighbors because you have the connectivity, and now you take your field. Let's say that each neighbor has some vector function defined on it. Some 3 dimensions at the first layer, but then, I don't know, 64 dimensions at the second layer. It's just a 64-dimensional vector at each of those neighbors. Right. Now you take your filter. And because I said permutation, you need to be permutation invariant, the easiest way to think of, I'll explain one of those, the backbone that we use for that work. You take your filter, think of a 1-by-1 convolution. So it's 1-by-1 by 64 in our case.
Okay.
Right?
I'm not quite sure how you got that point into 64.
No, I'm just saying that you have, at a certain point on a graph, right? You're at a point. Each point on that graph is a multidimensional vector now, right? At first, let's say it was a mesh at first. Each point on a graph was a 3-dimensional vector.
Right.
All right, that's the first layer. Okay, let's talk about the first layer. Now you're here. right? You have your filter. Your filter can take you from 3 to 64 dimensions. So you think of a 3 by 64 matrix. You take that matrix, you multiply by each of the neighbors, right?
Oh, okay.
You aggregate.
Right.
You put that value, that's your first dimension. Now you can take another one. You can do the same. What you can't do is you can't mix in images. You have the privilege to take a different, you can think of the same as an image, right? Where the connectivity is just a 3 by 3 neighborhood.
Right.
But there you have the privilege of always,
Yeah, you're convoluting.
always saying that the top left corner will get that weight and the one above me will get another weight. Here you can't say that because you can't commit to an order.
Right.
So you have to take the same weight and apply it to all of them and aggregate. That's hence the permutation invariance.
Maybe I'll read the paper.
We can take it
That's a good
offline.
start.
You can take it offline and I'll explain more deeply. Sorry, was a yeah.
We'll take 2 more questions, okay?
Okay, sure.
I was just wondering how you this was thought of before, how you like assess like the training sets of data, because I'm sure there's some kind of trade-off between completeness of data and like how broadly it represents like say like a person versus like depth of data, like like we could have lots of different kinds of pictures of people, but then there's not going to be that many, so we don't have enough data to work on to like create very thorough, accurate representations. So I was just wondering.
The easy answer is I take whatever I have. There's not a whole lot of data currently available in 3D. This data set that I showed here, this one, that's called, and again I said I should have cited the authors here, but this is the dynamic Faust. It was published half a year before I started working on this project. So one of the reasons I was excited that such a project can be done is because we finally have the proper amount of data. Until that point, the number of data of 3D meshes with deformations of people that we had were like 10 different figures at 10 different deformations each, right? So you can't even allow. Then we came up with techniques to working with limited amount of data, like working on pairs and and then you augment naturally the data because right you don't have 100 suddenly you have 100 times 100 because you can take each pair and treat it differently. So you have those techniques. So that question wasn't even, we didn't even have it in mind because with limited data you take everything you have, and that was the first time we had a little bit more. And what we did here is subsample the motions. These are sequences of people doing different activities. So we don't need every frame. But we took every 8th frame, every 4th frame, I don't remember. Yeah. It's also a question of which, you want to evaluate your set, right? So which activities do you leave out? What is considered to be a proper generalization? Yeah, it's yeah, one last question. Yeah.
I'm just curious, how many samples were in that set, and did you come up with any way to augment it effectively?
We didn't need to augment it here because we had enough. This one had, I think 30K different shapes. Yeah. Number of subjects though was limited as well. That is an issue. So that is something that needs to be taken care of. Right. Yeah, I think we're out of time for questions, but I'm still here. So yeah, I'm happy to.
Everyone has a chance to take the last slice of the pizza. Again, thank you all for joining, and we'll see you guys in the next one.
Right. Thanks.
So, somewhat new to this. I understand your convolutional network because you know where they are. You can give them different weights based on their thing.
Right.
But so you're saying something similar. So here we have all these points.
Right.
Now